Well, good afternoon, everyone. Nice seeing you all. Welcome to our second episode of season 5 of Enrich Your Coffee. And it's a great pleasure to have my ESS colleagues with us today to discuss neutrons. So the topic for today, it's a natural tool for industrial research. Unfortunately, Andrew Jackson, who is group leader and instrument scientist, couldn't make it with us today, and we wish him a quick recovery, and we hope to see him back soon. But the beauty of having two speakers is that Robin Woracek is here with us. So thank you very much, Robin, for your time. And so Robin is also an instrument scientist here at ESS, and I can't wait to hear him explaining why we choose to study materials with neutrons and what types of measurements are possible.
Yeah, so I will talk, the title of the talk is Neutrons, a Natural Tool for Industrial Research. And thank you, first of all, very much for inviting us to give a presentation about the use of neutrons for industrial use. And as I already said, my boss, Andrew Jackson, who was planning to give the presentation, is unfortunately out sick. So I'm giving this presentation on behalf of him. And as you heard, my name is Robin Woracek, and my background is actually in mechanical engineering. So I'm personally working, and my biggest personal interest is in working with mechanical engineering and metallurgy. And what I will show you in this short presentation now today is how neutrons can provide complementary and often very unique contrast when you compare them, for example, to X-rays or any other characterization technique, really. So I will cover some basics about neutrons and the different contrast mechanism that they can provide. And then I will say what neutron methods we typically use and at what length scales they operate. For that, I will then show you a small subset of examples and use cases. And based on that, we can hopefully engage in some discussion afterwards and some coffee. So let's start out to why we actually use neutrons first of all. Well, neutrons have some very particular properties that makes them very suitable for the type of studies that are of interest not only for pure scientific, but also for industrial applications. Neutrons themselves are charge neutral, which means they are deeply penetrating. Then they also have a magnetic moment, which means that they can not only probe material structures, but also probe the magnetic structures, for example. And then also neutrons are scattered by nuclei, which turns out to mean that they are especially influenced by, for example, light elements. And they can also even differentiate between different isotopes of the same element. And between all these things that I just mentioned, they then allow us to visualize, for example, hydrogen fuel cells, to design better superconductors, and to understand drug binding and enzyme actions, for example. So now typically everyone is more familiar with X-rays than with neutrons because they are much easier to come by. So I like to briefly review how X-rays and neutrons differ in their interaction with matter. Neutrons interact with the nucleus of an atom, unlike light or X-rays, which interact with the electron cloud. So you can imagine the nucleus to be the size of a marble, and then the atom is the size of a football stadium. And as a result, neutrons interact with your sample only when they hit the nucleus. And as a result of this, neutrons can penetrate, for example, this thick lead container that you see here with some flowers inside. And when you shine a neutron beam through it and take a radiograph, like you would just go to a doctor and take an X-ray of your arm, for example, with neutrons, you can then even reveal the flowers inside the thick lead container, because they contain a lot of hydrogen, which is actually the lightest element, and neutrons are very sensitive to that. If you look now at the radiographs here, there's actually a model engine on the right side and then also a rifle bullet. You can see how the combination of neutrons and X-ray can actually give a full picture of the same components, and neutrons see through the heavier metallic elements, but then are attenuated by the lighter elements. And these examples here on the macroscopic scale highlight already the unique opportunities that neutrons offer for us. A very useful thing generally is if you want to maybe decide if neutrons might be the right tool for you, is to look at this type of periodic table that compares attenuation for neutrons versus X-rays. And for X-rays, we have a proportional dependency on the elemental number, while for neutrons, the interaction appears rather unsystematic. And moreover, as I already mentioned, the interaction is different even for different isotopes of the same element. In this example here, it's hydrogen and deuterium. Deuterium is an isotope of hydrogen with just another neutron in its nucleus. And moreover, this attenuation, or more generally speaking, the neutron cross-section, also depends on the energy of the radiation. And this is true for X-rays as well as for neutrons. And of course, one can make use of these differences during experimental investigations, something that we inherently will do at the ESS because we are a pulse neutron source and we have energy selection by a method called time of flight. And then the total neutron cross-section, and this is how technical I will likely go in this talk, is described. So the total neutron cross-section is describes the observed attenuation by a material, and it depends on different scattering contributions as well as absorption. This is the formula that you see on the bottom right here of the screen. And then the scattering contributions can further be subdivided into elastic coherent, inelastic coherent, elastic incoherent, and elastic incoherent scattering. So we can investigate all these different processes taking place. And coming back briefly to the thing about the isotope sensitivity, if we take, for example, again, hydrogen and deuterium, again, deuterium being hydrogen with extra neutron in its nucleus, those are isotopes of the same element, but they have quite different scattering properties for neutrons. So when we can change hydrogen for deuterium in our sample or in our system, then we can often significantly enhance what we can get out from any experiment. And here's this type of experiment in a cartoon form. And you can see there sits Lola in her chair with her neutron refractive index carefully blended in, so she matches with the surroundings. And Harold, on the other hand, is sticking out with his choice of clothing. So when now the neutron monster comes, it's going to find Harold in no time and eat him up. This is where we can make use of selective deuteration. So we can make selected parts blend in or stick out. And this is now depicted as a more practical microscopic example using emulsion as an example. And let's say we have emulsion droplets in blue, suspended in a red emulsifier in a green solvent. And what we can do now is by changing the hydrogen deuterium ratio in that solvent is to make that solvent effectively red. So it has the same neutron refractive index as the emulsifier. And all we now see is the core of the emulsion droplets. Or we make the solvent blue, so it has the same refractive index as the core of the emulsion droplets. And we now see the emulsifier shells. So this is now an example where we can make use of this isotope exchange to highlight certain features of a system. This can be applied to a lot of different science cases and hence also industrial research areas. Next, I would now like to show you which neutron-based techniques we have available and how they can be used to study different materials under different length scales. And at ESS, I mean, all neutron sources that have scattering instruments have usually a suite of instruments. And also at ESS, once we start operating the facility, we will offer the most common neutron techniques shortly after we start operating the facility. Moreover, on the slides after this, I will try to give you more of a taste of the different type of experiments that can be performed using neutrons in order to answer some of the grand challenges of our time, for example, related to energy, material science, and health. This PR type of picture here depicts typical areas where neutrons already did and can be expected to keep making key contributions. And you can see that these areas span almost all things we really care about and are confronted with in our lives. And to be more specific and to give you now a flavor of what length scales we are talking about and what type of information you can get out, let's just put a rough length scale here on the x-axis. And then if you are interested in the atomic structure and or the magnetic structure of a material, then the atomic lattice spacing on the angstrom regime can be probed by neutron diffraction, whereas neutron reflectometry is a very powerful technique to investigate, for example, surface and interface structures on length scales ranging anywhere from the sub-nanometer up to the several hundred of nanometer range. And small angle neutron scattering can be used to study all sorts of substances on similar length scales as reflectometry, between 1 nanometer and up to a few hundred nanometers. Then these length scales, if needed, can further be extended by more specialized techniques towards a micrometer range by very small and ultra small angle neutron scattering. And all of these scattering measurements are performed in reciprocal space or Fourier space. And then we also have neutron imaging, which is actually performed in real space. And the accessible length scales are determined by the achievable spatial resolution of your instrument, basically, which is nowadays a few micrometers. And of course, neutrons can then shine through tens of centimeters of many materials, making it a very unique and powerful tool. Moreover, I should highlight that all these scattering techniques usually probe average volumes of the material, while imaging is a spatial technique that I just explained, so you get a real image of your sample. And here I would start out to show some examples related to neutron imaging in different science and also industrial research areas where that can be extremely useful. And most applications that I will now show on this slide actually exploit simply the attenuation differences between different elements and isotopes. And as such, one can, for example, study water uptake in this root soil system of a plant. And you can see in 3D and in live time, basically, how water is taken up between the roots and the soils in such a system. And of course, that can be important for biology, but also agriculture and different things that you may add to a soil and so on. Or one can also reveal hydrogen in metals. And here hydrogen embrittlement is actually a grand challenge in metallography, as it can cause very catastrophic failures. And it is still very poorly understood despite almost 100 years of active research in that field. And now, especially when we as a society move towards a hydrogen-based society, this may even become more important. And here I'm thinking about how the steel production will be done in the future, and if you're driving fuel cells cars and so on. And neutrons could really play a vital role here. Another popular application, also very important, is to look, for example, at lithium transport in batteries. And we just now are starting our project also here, where ESS is part of, on solid state batteries using combined X-ray and neutron techniques. And this is also a grand challenge now if you want to fight climate change and to enable better transportation. And due to its non-destructive nature, neutron imaging has also been extremely successful for cultural heritage applications. Here you can see, for example, a lead statue. And since the lead can be easily penetrated by neutrons, one can reveal the inner wooden kernel, and moreover, even locate regions inside that have been soldered or corroded. Applications, of course, also exist in the medical sector. Here you, for example, see a bone structure and implants. And of course, one can look also at larger assemblies, like, for example, this diesel particle filter. And for length scales that are actually smaller than the micrometer range, we then typically use other techniques than imaging. However, I like to point out that also imaging nowadays exploits scattering contrast mechanisms, so it's also sensitive to these other length scales. But given the limited time today, I will now show you one example each for diffraction, reflectometry, and SUNS for different use cases. So using neutron diffraction, we can, for example, study the atomic lattice spacing within materials. Here we are looking at the crack propagation in an austenitic stainless steel. And by using a small neutron beam, we can probe the d-spacing of the atomic lattices. And from that, we can obtain a strain map to answer how the crack tip propagates through the sample. This method can, of course, be applied to all sorts of alloys to study fundamental properties, but also to study industrial processes like rolling, forging, welding, and so on. And I believe Sandro Cabeza, who is also joining right now from the ILL, will soon give a talk in a month, I think, from now, how one can standardize strain scanning for industrial use cases, which is a very nice and great initiative. Another area where we can make use of neutrons is in agriculture and food science. This study here focuses on how antimicrobial and antifungal proteins in plants actually go about disrupting the cell membrane of microbes and fungi. And this is a major problem for some plants that do not have that kind of protection. But if one can now understand how the process works, then this potentially allows for genetic modifications or crossbreeding to improve these plants. Moving now to biotech and medicine. Here there's a strong field to study to looking at biomolecules in solution. They can be biomolecules in our body or in other species, and trying to understand how they behave is of course important in itself. But also in particular, people are interested in drug molecules and how they interact with molecules that are naturally occurring. Also things like antibodies can be studied. So a lot of the things we're actually dealing for within the last 2 years, really. This particular example here is now concerned with the structure of high density lipoprotein in solution, where small angle scattering was used to understand how cholesterol is bound with nascent high density lipoprotein and how it was bound together. And of course, high cholesterol is a problem in many countries. And if you can now understand the exact mechanism of that, then it has the potential to help you to develop drugs to counteract it. And these were the examples. Now there are, of course, plenty more, but given the limited time, I will conclude on this slide and trying to encourage people why they can use neutrons. And first of all, well, because they are a non-destructive probe of structure and properties ranging between atomic and macroscopic scale, then they're especially sensitive to light elements. They can moreover be isotope dependent, so allowing for contrast variations and to allow complex structures to be more easily understood. In particular, if you use neutron imaging, you can also reveal features that otherwise remain undetected, so any inhomogeneities. And also there are a lot of advanced techniques, and especially here at ESS, we will be able to perform really unprecedented in situ and operando studies in the future. And now I started to also boil the coffee for all of you. Thank you very much for listening. I would also briefly like to point out some presentations focused on industrial use of neutrons. And there are actually some recordings here on Vimeo that you can watch. And I'm open now to any questions. And you can also email Andrew, his email is there, or me anytime you like. Thank you very much.
Thank you very much, Robin. That's very interesting. I mean, a lot of possibilities indeed with neutrons and all the different domains that is covered. So, yeah, and I really like this this coffee example, like with the machine. I mean, I remember seeing it earlier. But maybe we will share also on our website and social media the links to the different videos you mentioned. So thanks for your time. Is there any burning questions for Robin? Please go ahead. Don't be shy. No questions. Does anyone have any experience? I mean, maybe Sandra, you want to say something because you work also with neutrons. So do you have any anything particular you experienced, or to jump on what Robin mentioned, or don't want to?
No, I could have 100 million questions for Robin, so that's why I didn't want to maybe to jump in with all of them. No, so maybe regarding this industrial applications. So because I think in all neutron and synchrotron sources, we have this parallel industrial offices and like parallel industrial access. But is there any discussion also at the ESS level to have industrial research, let's say non-confidential or non-paid industrial beam time?
Yeah, we are still, that's a very good question. We are still discussing our access routes really to enable that. And there absolutely is a plan. I also see Maria actually here, who gave a talk on, I think a presentation earlier here about this in Sweden. Venova offered projects with industry partners, and we see actually a big interest of industry to use neutrons. And for one thing, we would like, for example, to engage with industry to engage in certain sample environments that we like to put, for example, a thermomechanical simulator to put on beer, which is our engineering diffractometer. And for that, we need to counter offer, of course, something to the industry as well to have that. So we are engaging in discussions, but it's not fully decided yet, but there will definitely be the opportunity for industry to perform confidential research. I think I can say that is definitely in the plan.
Okay, yeah, that's good.
And how many, I don't know if you have a number handy, Sandra, how many industrial users you have percentage-wise on SALSA, on your instrument?
Yeah, this is why I think the discussion is very interesting between us all, because so we tried for a while at TLL to have 40% beam time for industrial collaborations. So this was not only paid, but as you said, to develop new experiments, new in situ systems, and to share students. And we saw a very positive response. So we saw a lot of interest, but this was, let's say, a punctual action. So I'm also aware of this Venova projects, and I also think that kind of stabilizes, let's say, this research at synchrotron and neutron sources, and this allows you also to perform in the long term, right? Some these industrial developments that cannot take care in 1 year, or the learning curve is 1 year, then you exploit it the following 3. So that would be very interesting. So at the moment we have 30% together with the European projects. So what we did is that we aligned with industrials in a European project, so that we can of course publish the data, because this is also what we are aiming for. And this was very, like I said, so very much appreciated, because they do not care not to measure the last status of the component they are going to sell, but they care about the learning process, right? So if they can learn faster, end of the day, they could sell it faster, the final product as well. So we had a very good experience in that sense.
That's great. That matches a bit also what my experience is. We just had a discussion actually now in one of these Venova projects I'm involved in with a Swedish company. And what's really interesting is, I mean, many maybe scientists or academics say, oh, this is kind of maybe boring, like industrial thing, but actually it's the opposite. Like actually the use case that they have is really pushing our methods to the absolute limit.
Yeah.
And we got declined a beam time on one proposal. Luckily, we got another beam time, because it said, oh, this is just industrial thing. But in the resubmission, we will make clear this is actually the opposite. We need to push the methods, like they are looking at phase fractions that are actually really challenging. So it's really nice to get these people involved with those questions to then actually push our methods on another level.
Because they have another level of exigence, right? So they demand other things. So in our experience, for us, it was the same. So we always got rejected a few proposals because they said this was too applied or not fundamental enough. And we said, look, we are moving for plates, from welded plates to additive manufacturing. This is already a jump, a huge jump, and this is being pushed by industry. I mean, the academics, of course, we want to understand maybe more the fundamentals, but the industry needs to understand the final component as well. So they are really pushing on that. I totally agree.
Maybe I can add 2 things also from the Venova funding scheme, that you can't see in the resulting one-pagers that you also that if it was paid access or not. Most of the projects have actually been allowed peer review for their operando in situ studies also because of the novelty. So they have been quite high success rate. And several of the projects also take that for granted that they will actually receive it. If it wouldn't have been for the pandemic, of course, it would have much more gone through already. But I think what's also beneficial from our setup is that we are engaging collaborative research support from that the industry is already working with lab-based techniques. And they are the ones also explaining about the possibilities and are ambassadors and set up this project in the first place also. So that's been a good benefit to be able to provide funding for the intermediates in the work. Thanks.
Yeah, it's interesting to hear. Just checking. Yeah, it's interesting to hear that industry can actually triggers and push the boundaries from, you know, the on the research side, and, you know, like somehow like challenge the scientists and the way you're going to use the instruments and how you're going to work actually. And so it's quite interesting. Is there anyone with some kind of industrial experience on this type from the audience, or like, or more comments or other questions? Or
I think the last comment I had based also on Maria's input is that we see the difference when the industry gets financing, gets support, right, for research. So they have some internal financing, especially like medium-sized companies. They have a very limited research budget, so they cannot allocate it for neutron synchrotron measurements. But whenever there's some help in the financing, and I'm talking maybe only about students, this makes a difference to develop things with them. So I think that's why I think that the best example for me was the Venova case, because once they get help, they are very happy to develop things together and to publish things together.
And do you monitor the number of industry demands you have, or especially from the SMEs, when you can, or when they have this capacity to have funding support? Do you see like a raise in the demand, or?
Yeah, it's basically the decision towards yes or no, basically to develop something they cannot invest sometimes.
And do you have enough beam time to offer them when you have a lot of demand, or can you answer the demand?
Yeah, so this is at the direction level as well, right? So if for certain instruments like imaging, Robin was showing SAMs and stress scanning, they are highly demanded. So there's a minimum of 5%, but depending on the cycle, if they need to reallocate a bit more beam time on top, they can decide to do that.
And Robin, do we have already at ESS an idea of the percentage of industrial use, or is it still like in the consideration?
I think it's in the consideration. It's as far as I know, it's not fully decided yet, but the access routes have been laid out and there are proposals for that already. But for sure, will always be possible, as what Sandra mentioned. I mean, if industry is engaging in collaborations with a university, then I think it's fairly easy. And in most cases, I think, at least from my personal experience, industry is mostly fine with that. And that will also, yeah, I mean, maybe if there's a shared PhD student, I think is often the most productive way to carry on something longer than just a few months. So I think that is very, I mean, if we can come up with those kind of models, that's really the most productive one. And then, of course, maybe some industry are now, for example, at Paul Scherrer Institute, one group is actually financing even their own personal from paid industrial access. So they are very routine things where some industry need to repeatedly look at their parts with neutron techniques. It's often actually fairly simple radiography, and they are paying for that. And then the groups can use that money for something. So I know like there are certain use cases, they are rather specific, but where that exists for sure.
You could also consider like fast access, paid access, and then long-term developments, because every case might be a bit particular. For us, when we have found some trouble, and now especially since Munich is also down for some time and ILL is in a program shutdown this year, is to have a reallocation, right, of these industrial uses somewhere else fast enough, because if you tell them to wait 1 year since you prepare the proposal and you get beam time and so on, this is sometimes not enough, or they're not really happy with this, and then they just forget about neutrons in this case.
But I can add also one thing, that the industry who's been taking part in the Venova project, this is actually mostly large companies who also needs to be engaged in using this and to see the value in order to make investments, and can also provide a path waits for smaller ones, is that they have been quite prepared to wait for 1 year in order to access, and they also learn that is kind of built into the system when it comes to the research and development part. of course, there might be other situations also. So that's also something that learning about the value from actually trying, but not hesitating to do it because they already had a shot at it and saw what it could provide, apart from what you can obtain in the laboratory sources.
But you can imagine then, I mean, we're running out of time, but you can imagine that when the industry needs to wait, then probably, I mean, something they should be aware of and try to anticipate as much as possible if there's a delay, because usually, I mean, what I understand is like there can be a clash in between the timeline of an industry versus what can be offered by a research infrastructures. And this is usually where you find the clash. So maybe if you educate industry on anticipating as much as possible, which is very different from them because they are really like in the short term most of the time. But maybe that can be something to be discussed with them on some specific activities, maybe, or when there's no possibilities to offer them like quick access or. Okay, well, so very interesting discussions, and I'm looking forward to see how industrial users will come to ESS and what's going to be done. I mean, that's. It's fantastic. So if we don't have any more questions, we'll close the session. I will just remind you that registrations are already open for next month. And so Sandra, who is with us today and has been very active, now you totally rehearsed for 1 month, for next month, and you will come back to talk about the neutron quality labels. The label that has been developed under together with the support of the Brightness 2 project, but I'm not going to say more about that. So I invite you all to register already. You have the link. Thanks, Madison. And I wish you a great day, and I see you next month. Bye.
Thank you very much.
Thank you for coming.
Good day.
Bye.
Bye.